So the last thing that we did, we just proved that using the contradiction method, proving that the radical 2 is going to be an irrational number. Okay, so the idea is contradiction method. So we assume that it's not true. This means you assume otherwise, that the radical 2 be a rational number, and then you try to arrive at a contradiction. So the idea was, if it is a rational number, so it must be in the form of the a over b. It's a fraction, we always able to simplify it so that we get to the case that this a over b is going to be in its reduced form. So a and b won't have any common factor or common divisors. So we work out in this one, we arrive at the fact that the a and the b, both of them are going to be even number. So when they are even number, they have a common factor or common divisors, which is going to be 2. So that would be our contradiction. So we get back to the original assumption. So our assumption that the radical 2 is a rational number is false. So radical 2 must be irrational. Okay, so that was the first part that we did. Any question? Now there are a couple of problems related to this one. Okay, and that give you a method that you can generalize it for more general problem. Okay, so these are the main examples that we have. So we're going to continue. Basically, it's going to be the fact that the sum of a rational number and irrational number is always irrational. The product of a rational number and irrational number is always irrational. Okay, so you must know this one. It can be proved by a contradiction method. So first we go with the numbers, and we have it in general in your next review. Okay, so you are going to be asked to prove the following by contradiction. A very popular problem, and you get various format in your assignment. So there are two cases. The first one is that 5 plus the radical 2. You see 5 is a rational number, radical 2 is irrational. So the result is always irrational. Okay, that's one. And then one with the product. The difference and the quotient is going to be the same. Both of them are problems in your assignment. You just copy this type of solution proof that we have. The next one, you see this is a rational number and the radical 2 is irrational. If you multiply them together, the result must be irrational number. Okay, so that's what we want to prove by contradiction method. So as usual, you assume it's not, and then you try to arrive at a contradiction. Okay, are you ready? Getting the first one. Okay, the first one, we assume not. Say suppose not. Okay, suppose it's not true, or suppose not. Suppose not means this is a rational number. So you assume. So assume that otherwise 5 plus radical 2 is a rational number. Okay, is a rational number. So write the definition of a rational number. So there is going to be, there is an a, okay, integer, and there is a b, of course, with the condition that the b is not equal to the 0. Okay, such that 5 plus a radical 2 is going to be a over b. See, that's going to be, if you don't believe that this is an irrational number, so that might be the conclusion. So what you're going to do, you have to arrive at the contradiction. You see, the contradiction is coming with the fact that you know that radical 2, if it's going to be radical 3, radical 5, we accept all of them on the test, okay? You don't have to prove it. So what we are going to do, you can isolate the radical 2 here. Then you arrive at the contradiction. You see, this is going to be the case. So if you keep the radical 2 on one side and then subtract the 5, so that give a over b minus, okay, minus 5. Okay, minus 5, and you can, we can find the common denominator if you like. So you write this one's 5b over b. Okay, so this is going to be like a over b, and this is going to be 5b over b. Okay, and this is the difference of two fractions. So the radical 2 is going to be equal to what? Is equal to the a minus 5 over b over b. You see the term to the right, the top is the difference of two rational numbers, which is going to be rational, and the b is not equal to the 0. So the terms to the right is a rational number. Okay, so this is rational, and you know that this is irrational. Irrational. So that is the contradiction. You see, to have a rational, irrational number to be equal to the rational numbers. So our assumption is wrong. So you can claim that by contradiction. Give us the method. By contradiction, you see, 5 plus radical 2 is irrational. Irrational, and we are done. That's a proof. Any question? So we're just using the fact that here, we just simplify it. You see the difference of two rational numbers is going to be a rational number. We talk about it, but we just proved it over here. And we know that the radical 2 is irrational. Okay, that's it. This is the sum. In your book, you have 5 minus radical 2 in your assumption, in your assignment. It's the same thing. It's going to be, this would be maybe a plus here. Okay, any question? So that's the first part. We do the similar operation for the second part. Okay, so that's a proof of the second part. In the second part, you want to prove that 3 radical 2 is irrational. Again, you suppose not, contradiction method. Suppose not. You assume that it's not true. Suppose not means the other way around is true, so you assume. Okay, assume otherwise. You have to give us this assumption, okay, to start with. So you assume that the 3 radical 2 is going to be what? Is rational. Again, definition of the rational number. There is an A, there is an B, with the condition that the B is not equal to the 0, and this 3 radical 2 is equal to A over B. Okay, a rational number. Again, you try to isolate the radical 2. Any suggestion? What's going to be next step? To isolate the radical 2 on one side of the equation, everything else to the other side.
Divide both sides by 3 or multiply by 1/3.
Very good. Yes, we divide by 3. So that would give us the, okay, this is it. So that gives us a radical 2 here. And if you divide by 3, that gives A over 3B. You say A over 3B is going to be a rational number because B is not equal to the 0. 3B is not equal to the 0. So quickly you get your, okay, quickly you get your contradiction. So you claim that this is a rational, and we know that this is irrational. So that is a contradiction. Okay, it's a contradiction again. So you claim that by contradiction, you have to mention the method. By contradiction, original one. 3 radical 2 is irrational. Irrational, and you're done. See, that's going to be the one. Any question? The division is going to be the same thing, if you have one in your book. that it's going to be radical 2 over 3. Again, it's going to be irrational number. It's the same thing, we divide by 3 to get to the rational number and irrational number. In that case, you may have to divide to get this number. Okay, any question? Of course, you can generalize it, and that's the one that you are going to have in your next practice one. 5 and radical 2 was not important really. So you can generalize it, the first one, into the fact that the sum of you can call this one R, a rational number. This is X, irrational. So you can prove that the sum of a rational number and irrational number is irrational. You do the same thing here. You see, you isolate the radical 2. In that case, you isolate whatever it's given to you, and they call it irrational. So over here, use the fact that the difference of two rational number is a rational number. Okay, so it's going to be the same procedure, and we are going to take care of it. Okay, any question? So this is just to give you an idea how we deal with this type of problems. I give you a couple of more because you have a similar one in your book. You just want to make sure that you know how to handle these problems. So that would be, you have a group of them in this format. Number 3. Number 3, you want to prove that for any, okay, for any integer, n, okay, for any integer n square minus 2, n square minus 2 is not, okay, is not divisible by, okay, is not going to be, is not divisible by 4. And you have this different formats. And there is one point regarding this problem that we can use it in a more general form. Okay, I explained that one too for you. Okay, so for any integer n, okay, for any integer n, we want to prove that n squared minus 2 is not divisible by 4. Remember, you cannot give us any example. I give this one on the test, and some people, they give example. No, you have to prove it. Prove it by contradiction. Okay, so what we're going to do again, we suppose not. What does it mean? Suppose not means there is a n, this n squared, okay, n squared minus 2 is divisible by 4. Is divisible by 4 means a multiple of 4. Then you try to see if you can arrive at the contradiction over there, okay? So the solution is going to be, again, you assume otherwise. Suppose not. Suppose not means you assume that. You see, you assume that n is an integer and n squared minus 2 is divisible. Okay, you assume that this is divisible by 4. And we have to work on this one to see how we arrive at a contradiction. Okay, divisible by 4 means it's multiple of 4. So this means that there is a k such that n squared minus 2 is going to be equal to the 4k. Okay, there is an integer such that n squared minus 2 is a multiple of 4. Now let's say we're going to arrive at the contradiction. Okay, so what I'm going to do, I'm going to isolate the n, or just solve for n. So that give me n squared. Okay, that give me n squared equal to the 2 times 2. Okay, sorry. It's going to be 2 plus. Okay, I'll just move it to the other side. 4k. So n squared equal to the 2 plus 4k. Okay, I add the 2 to the other side. Then I can factor out the 2. So that give me n squared equal to what? Is equal to, I factor out the 2. So that give me 2 times what? Times 2k plus 1. Okay, 2 times 2k plus 1. And this is going to be a contradiction. Any suggestion? I can go on one more step if you like. See, I can go one more step. I can find the n if you like. I find the n would be a square root of 2 times 2k plus 1. Okay, 2 times 2k plus 1. So this is going to be a contradiction. Any suggestion why it's a contradiction? Remember, k is an integer.
It's because it's not an integer,
It's
right?
not, why it's not an integer?
Because it's a rational.
No, why? Just better explanation. We know that we have to prove this is going to be, this is not a rational number. So can you give us a strong reason? That's why it's not going to be. You know that.
Maybe
This, yes.
someone.
Okay, let's see what we need to prove. Okay. You see, what you need to know is you should be able to take this one outside the radical, because you are right, because n is an integer. Yes, this is it. This is true. N is an integer. Okay, this is integer. So if you can prove that you cannot take this one out of the radical, then you are right. You see, so basically what you need the inside one to be a perfect square. You see, if this inside is perfect square is like 9, 16, 25. Okay, if that inside one is going to be a perfect square, then we can take the square root. Then that would be integer 2. So you have to prove that. You have to give us a strong reason why 2 times 2k plus 1, k is an integer. 2 times 2k plus 1 is not going to be a perfect square. Any suggestion? What type of number is 2k plus 1?
It's odd.
Is that? That's it. And what type of numbers is 2?
What's even?
Even. You see, in order to get to the perfect square here, the perfect square, both of them must be even odd, or both of them must be even, because you need a perfect square. So this is a 2. So to make it a perfect square, you need a kind of a 2 again. So 2 times 2 would be 4. And if you think about 2k plus 1, 2k plus 1 is an odd number. It's like 3, it's like 5. So in order to make that one to be a perfect square, you need a similar one. You need an even number, you need an odd number. So it's going to be 3, you need another 3. 3 times 3 would be 9. So it never happened, because one of them is even, 2 is even, 2k plus 1 is odd. So if you multiply an odd and the even number together, you never get a perfect square in this case. So this is not going to be integer. Okay, so this is going to be irrational or non. This is irrational number. Okay, it's going to be irrational, or it's non-integer if you like. Non-integer. Okay, so the explanation is going to be 2k plus 1. 2k plus 1 is odd. Okay, it's going to be odd. And so this is it. 2 times 2k plus 1 cannot be a perfect square. It's not like a x squared and a squared. Okay, it's not a perfect square. Perfect square. So when it's not a perfect square, means you cannot pull it out of the radical. You see, to be able to pull it out of the radical, you need something like radical 16. It must be odd, or that's going to be even to get, to get these numbers. Or in this case, you cannot have it to get this part here. Okay. So the reason is that the 2 here, you see, you have the 2 here. So you need another kind of a power of 2 to be able to take care of it. It's not possible. Okay, so any question? I gave you this one because this is one of the problem in your book, but you have a better one in one of the assignment, and all these problems coming from that number. So I just show you, probably when you read it, you will have either a new edition. They just they switch this problem, but I think it must be there, either the first one or the second one. So I give you the address. This is 4.7. It must be number 15. Okay, this is a kind of most general one of these problems. So what is the most general one? Oh, okay, I just didn't finish this one, sorry, you know that. This is going to be 2k plus 1, so we get a contradiction. So we have to say that by contradiction, by contra. Okay, so by contradiction, what was the result? N squared. N squared minus 2 is not divisible by, is not divisible, is not going to be divisible by 4. Okay, so not divisible by 4, and that's the difficulty that we're going to have. Any question? Now this is much more general than the one that we did over here. This is that problem that we have. Let's write it down and explain it. What is the problem? The problem is if A, B, and C, okay, 3 numbers. If A, B, and C are integers, they are all integers. They are integers such that Pythagorean identity, that's it. A squared plus B squared is equal to the C squared, this identity. Okay, so we have 3 integers that satisfy the Pythagorean identities. If this is going to be the case, at least one of A or B must be even number. Then at least A or B must be even, is even. So this means if both of them is going to be odd, it's not going to be possible. It's the same problem. Okay, so we have 3 integers. We have 3 integers satisfying this condition. A squared plus B squared equal to C squared. Then we want to prove that at least A or B must be even. This means one of them is even or both of them are going to be even. That would be fine. Okay, so that's interesting. And when you write the proof, you arrive at the same condition that we did over here. Okay, everybody happy about the problem? So we want to prove it by a contradiction method. So it's very important to see how you start. Okay, so let's see. So the contradiction method. So the solution is going to be, this must be the starting point. You suppose not. Okay, suppose not. Suppose not. So suppose not means you assume that this is false. So the other way around must be true. Okay, so the negation of this statement must be true. What's a negation of this statement that you want to assume? You know that you have to assume that, you see, you have to assume that the negation is going to be true. Any suggestion? What's going to be the negation of this statement? Because their statement is if A squared plus B squared equal to the C squared, then at least one of them, A or B, must be even. So what's the negation of this statement?
A, B, and C are integers such that A squared plus B squared equals C squared, and neither A or B is even.
Which is the same as? It's going to be the same of what? The same as, yes, your neither means what? This means both of them are going to be odd. Okay, so that's going to be the assumption. You suppose not. Suppose not means the negation must be true. The negation of the or would be and. That's it. It's going to be and. Yes, not A and not B is given. Yeah, that's going to be one. So we assume that. We assume that A and B are going to be odd, and they satisfy A squared plus B squared, because this is at least A or B. You know that this would be changing to the what? Changing to the A and B. A and B, and this is even with the change to the odd. So that's it. Suppose not. So we have to assume that A and B are odds. Okay, are going to be odd numbers. Okay, odd numbers, and of course they satisfy that condition. And what? And we have the fact that the A squared plus B squared is equal to the C squared. Okay, now we have to work on this one to get the contradiction. So now we know what's the definition of the odd number. That's it. You see, A is odd, so there is a, let's say K1, because we have to use 2. K1 such that A is equal to the 2K1 plus 1. That's for A. Then for B, there is a K2 such that B is equal to the 2K2 plus 1. Okay, substitute here to see if you can get your contradiction. Okay, so what we're going to do is we're going to substitute here. So we have the A squared, we substitute, that gives us a 2K1 plus 1 all squared plus, and that would be 2K2 plus 1 all squared, and this must be equal to the C squared. Okay, now work on this one to get the contradiction. You can square it or just FOIL it. So it's going to be a square of the first one, which is going to be 4K squared, K1 squared, twice of the first times second, 2 times 2, 4. That gives you 4K1 plus the square of the 1, which is 1. So that would be when you square the first one, which is FOIL it. Then you continue, you square the second one. So that give you, okay, that give you 4K2 squared. Twice of the first time second would be 4K2, and the square of 1 would be just 1. Okay, so that's going to be the square of the second one. And this is going to be equal to the C squared. C squared. Okay, so combine the like terms. So we have a 1 and 1 here. Make it into the 2, and write everything else together. So we can see it is a 4K1 squared, 4K1. Then I have 4K2 squared, and I have 4K2. This 1 and 1 would be 2. You see, they are all together. Then I have a 2 here. That make it to the C squared. Okay, I just combined the 1 and 1. So all of them are divisible by 4. So pull out 4 as a factor. So what you have, it's going to be 4. I got the 4, the leftover is going to be K1 squared. Okay, K1. Then I have a K2 squared. Then I have a K2 plus 2 equal to the C squared. But they are all integers. So what I'm going to do, I'm going to call this one K. So what I have a 4K. I have a 4K. 4K plus 2 is equal to the C squared. Okay, if you factor out the 2, that take you back to the previous problem that we did. It's a 4k plus 2, so factor out the 2, so that gives 2 times 2k plus 1. Okay, so we arrive at the fact that the c squared is equal to the 2 times 2k plus 1. So we take the square root 2 times 2k plus 1, which is a contradiction again. Why? Because c, remember the c is an integer. But as we did it for the previous problem, 2 is an even number, 2k plus 1 is odd number. So when you multiply together, you're not going to get perfect squared. So the term to the left is an integer, the term to the right is not. So we arrive at a contradiction, okay? So I just put it here so that you can see it. You see that's a c, like the previous problem that we did. 2 times 2k plus 1. So this is an integer. This is not, because this is irrational. So that gives you a contradiction. So therefore, you get back by contradiction, show that your A or B, one of them must be even. You cannot have the case that both of them are going to be an odd, odd numbers. So A or B must be must be even. So it's a very nice problem, nice techniques that we use. Both of them are going to be in your book. You have a collection that give you something like 4 or 5 problems, and all of them of these, these categories. So get to know it. It's nice. It's different from the other problems that you do, so that give an idea of how we're going to handle if it's going to be a problem which is going to be a little bit more, more involved. Okay. Any question? So that's a contradiction method. It's a very, very popular methods, and we are going to use it as we go on. The contradiction one. So you always assume that the result is false, but you got to be careful, because when you assume the result is false, you usually have to consider it's a negation to be true. So that negation, make sure that you get it right to write it down. Okay. So check the problem of this section. Some of them are, a couple of them are very tricky one. You can bring it up if you need any explanation. That's the most tricky one that you see on your assignments. But if you see anything, just bring it. I can explain it for you. And when we get to your review, somehow we put these over there too. Okay, to get this. This is A, B, C, R in general. It's like a theorem. And so you can, you can check some numbers and just put them together. It's the same idea. The 2 times 2k plus 1, that was the tricky part. It's a product of an odd and the even number, 2 in particular. So the product cannot be a perfect square. Okay, that's it. We are done with that section 4.8. So we talk about all methods of proofs. Okay, to get through these very important sections. Yes, what's the question?
So in the quiz or a test, would we have to prove that 2 times 2k plus 1 is irrational, or can we just use that knowledge?
No, as soon as you tell us that the 2k plus 1 is an odd number, we accept it. Like that, since I did the same one for the previous one, I didn't have room to explain it, but this is your explanation. Okay, so you have to tell us that the 2k plus 1 is odd. Okay, and so 2 times 2k plus 1 is not a perfect squared. Okay, that's why I give you this problem first. Yeah, you have to just tell us that 2k plus 1 is odd. It's clear that then 2 times 2k plus 1 is not going to be. Yeah, you have to add this line. Okay, you have to add this line for both problems to get this done. Okay, any question? So get this one, have a look at the one that you have in your practice one of that section 4. I think it's 8. All your nice problems are going to be on that section 4.8, the best part. And I collected all of them in your next review, but just have a look to see if you have anything need more to be explained, just let me know. Okay, so what we're going to do is, there is one more section over here, and that's about this type of ideas. We want to put it in action. We put it in action in the case of the graphs. So that's why we are going to pause. We go back. Remember, there was one section, 1.4, about the graphs. I didn't cover it because we need it now. So what we're going to do is we are going to cover that section first because we need the introduction of the graph. And then we apply it to get through the section 4.9. There are a couple of nice theorems. And the reason is we bring it here. If you go to the old edition of this book, there was nothing at this section, okay? So that's a new one. So that will help us. At least we have something from your own field to see how we're going to apply these results, okay? And it's going to be easy. You get a couple of questions on that one. So we get back to the 1.4, we get the definition of the graph. And then when we are ready, then we come back and finish for 4.9. Then we are done with this chapter 4. And then we try to see if we can start chapter 5. Okay, so let's go back and for a change, get the idea of the graph from 1.4, and then we come back and we finish this last section. Okay, so going back to the 1.4. Okay, sometimes I teach that one at that time, and sometimes we teach it now. So in your case, we didn't get time, so we do it now. So just idea of the graphs. Probably you have seen it, or you may see it in a couple of your computer science courses. What's going to be the graph? You know that we already talked about graph, but when we talk about graph in calculus, we mean a graph of the function. So it's going to be a collection of points in calculus. A collection of points, x and the y, that satisfy the equation of a function. So that would be a graph of the functions. But in this case, it's going to be quite different. When we talk about the graph, we mean a collection of points. Okay, the collection of points, then we refer to them as vertices. Okay, and the collection of lines that going to be between these points. So it's going to be the collection of points called vertices, a collection of lines between the points. We call them, sometimes we call them edges, okay? We don't call them lines, okay? And sometimes we call them arcs. So we put them together, that would be the graph that we're going to talk about, okay? So if you think about it, look at any map, any road map is a graph. So the road map is going to be the graph. The vertices is going to be name of the different cities. Okay, and between those cities, there are some roads, if you like, or freeways. These are going to be the graphs, okay? So we're going to introduce some terms of the graph and give you one application in 1.4. Then just a introduction to the graph theory, really, okay? It's a very modern subject, if you like. And because of your discipline, computer science, the graph theory today is just, it's a field, one of the topics in mathematics. Years ago, it was not so popular. When I was a student, there was only one course in graph theory that we usually take. And the computer science, it was just in earlier stages. So we have only one course in computer science and one course in graph theory. Okay, but today it's quite different. You can get a PhD in graph theory, and it's a special field. And you know that its application in computer science is huge. Okay, so this is just a kind of introduction to the graph, because we want to get to know it and to prove some theorems using these ideas that we talk about. Okay, so it's nice that questions going to be nice when we get to the test or the quiz. So you should expect something like, yeah, it's going to be 3 questions in your next test and a couple of them in your next quiz. Okay, so let's get the definitions done, then we get to the theorems that we would like to prove. So a graph, the definition, a graph G, we call it. G is going to be consist of 2 things, if you like. The first one is the collection of points. So we call it the vertex set. We go with the V for the vertex, whose elements, members, whose elements are called, are called vertices. Vertices, sometimes we call them nodes or points. I go with the vertices. Okay, it's going to be set up points, set up vertices. Okay, that's one, but there are going to be lines between these. So the second part is going to be the edge set, edge set E, or we're going to be set of edges. Okay, set of edges connecting pairs of points. Okay, pairs of vertices. Okay, you don't have to have these edges between any two vertices, but if you have it, you have an edge. Okay, that's what. Now, sometimes you have some direction. So if the edges, all of them, if the edges are directed, then your graph is directed graph. Then, like the flow chart, okay? Then the graph is going to be called, it's called a directed graph. Okay, it's going to be a directed graph. Okay, that's going to be one. And of course, each edge or each line is going to be a connection between two vertices. So we have to tell you that each edge is associated with a pair of vertices. Okay, so it's going to be the definition that we are going to have. Okay, collection of points and the lines in between. That's it. That gives you the graph. So give you an example to see how we identify these terms. So suppose this is a given graph. This is it. So this graph would have 4 vertices. The vertex is going to be A, B, C, and D. So this is going to be usually denoted by V equal to a collection of points A, B, C, and D. Okay, so that's a vertex, vertex set. Then you are going to have some edges. So this is the way they are going to label it. For example, E1, E2, E3. It's going to be labeled, or you are going to label it, E4 and the E5. So your edge set is going to be, have the E1, E2, E3, E4, and E5. So this graph would have 4 vertices and 5 edges. There is no direction between those, okay, those vertices, if you like, those edges. So this is it's not going to be a directed graph. Okay, it's going to be undirected. Okay, directed graph. Okay, any question? But they may change it into the directed one, so they have to give you a direction. There are some purposes that, you know, your directed one is going to be A, B, C, and D. They give you some direction, like you see, this is going to be the one. So that's going to be a kind of directed one. So in this case, when you want to talk about the edges, you have to tell us this edge is going to be DC. Okay, DC, between D and the C. And this is going to be between C and the B. Okay, so just go with the direction. So this is the one we call it a directed graph. So that's a directed graph, and the other one is going to be undirected one. Okay, any question? So there's going to be a reason that, you know, you are going to direct them together, and then we are going to use it later on, and you will see it. So the roadmap, you know, that any roadmap is going to be a graph. If you go and buy a ticket, you know, airline tickets, they give you, you know, you have a map, and they give you all the direction, okay, and you can see it, and you can decide, you know, which one are going to pick, one which is cheaper, okay, or the time is going to be the least time that you have to spend, etc. Okay, so this is going to be the definition of the graph. Any question? Now, there are some terms that we're going to use to be able to give you some theorems. The most popular term, we are going to stay with the not a directed one, okay, because a graph without, because when you get to the direction, you have to modify your definitions, okay. So I stay with this one and give you some definition of the graph. And so the most popular one is going to be each vertex would have a degree. Okay, the degree of each vertex is going to be a number of the edges that's going to be okay, going through that vertex. So for example, the degree of A is 2 because you have 1, 2. But the degree of the P is 3 because we get 1, 2, 3. Okay, so it's going to be called the degree of the vertices. And that will give us, you know, a nice theorem in a minute. So let's define what's going to be degrees of everything we want to talk about. All the theorems depends on the degrees. So that's why we go with this definition first. So what is going to be? What's going to be degrees? Okay, so the degree of each vertex. Okay, the degree of a vertex. Degree of the vertex V is going to be denoted. Okay, it's going to be denoted by degree of V. And it's going to be the number of, okay, is the number of, it's going to be number of the edges that are going to be through that vertex, that are going through or incident. Okay, incident and at the V. So the number of the edges going through a vertex is going to be called the degree of that vertex. Okay, and what you want to do with the in a graph, then you have to go through this idea. Okay, so for example, just go a quick one. So if you consider this graph, the one that we talk about it, and this is going to be, so we have the vertex A, B, and that's going to be C and D. This is the given graph. Okay, so that would be the given graphs. So what we can do it, if you want to find the degree of each vertex, you see in this case, the degree of A is going to be 1, 2, because there are 2 lines passing through the A. And it's going to be degree of the B. Degree of the B would be 1, 2, 3, so that gives you 3. Okay, that's going to be degree of the B. Then degree of the C is going to be the same thing, that gives you 3. And the degree of the A. Degree of the A is equal to 2, and the degree of the D is also equal to 2. Okay. So it's going to be the number of the degrees that we're going to have. If you add all these degrees together, you see, add them together, you have a 2 and 3 would be, it's going to be 6 and 2 would be 8. And that give you 10 and 12. This is going to be twice of the number of the edges. You see the edges, you have 1, 2, 3, 4, 5. So that's, we must get, oh, I'm sorry, I write the 8 twice. Because if you add them together, that gives you 10. That would be 10, and this is going to be twice as many as edges that we are going to have. Okay, so this is going to be a theorem. That theorem is going to be 4.9. So let me just give you one thing more from this. I could come back and give you that theorem, because I want to finish that 1.4 first. Okay, so this is going to be the degree. Any question? Now, at this level, because this is just, we're talking about history of graph theory. The history of graph theory starts with the problem that we have something that we call it coloring of the graph. So what's going to be coloring of the graph? You can color a graph by using a color for each vertices. Okay, so this graph is given to me, so I can color the vertices over here. We can color it so that if you have 2, we call it adjacent vertices. If you have 2 adjacent vertices, they would have different colors. Okay, so when we talk about coloring of the graph, we mean we are going to assign a color to each, a color to each vertex, so that if 2 vertices are going to be adjoint, okay, then they should have a different color. Of course, you know, you can use 4 color and just color this one. But the one that we are interested in is the minimum number of, minimum number of the color that's required to color this one. And that minimum number is going to be called chromatic number, or coloring number. Okay, they call it coloring number of the graph. So that is one of the earliest problem in the case of the graph theory. You see, in application, that coloring is just an excuse. So if you can use it in various format. The things is that you see this A, B, C, D. Suppose there are 4 different subjects: English, mathematics, biology, history. And you are the manager, okay? You are the instructor or coordinator. So what you would like to do, you would like to design a schedule for the final exam. If you want to get a final exam, you see, if A and B are going to be adjacent, so they have the same students. There are going to be some students that student would have mathematics and history at the same time. So when you want to design the exam, you must make sure that they are not going to overlap, because the student can be present for one exam only. So the idea of the coloring, you are going to be the name of the, the name of the date that you need in order to give the exam. So this is the way we are going to use it in different programming, if you like, to be able to do it. And this is, we usually give you one and we ask you to do it. So I'm going to do one example to show you how to do the coloring, and then you can use the coloring one to get a kind of application problems, okay? So this is the idea in 1.4 only. So let's give you the idea. And this start with the problem in graph theory that we call it 4-color problem. The 4-color problem is that if you consider any map of the world, and you consider these vertices to be countries, and you are going to have the edges if the countries are having a same border, they are neighbors. So these are going to be different countries, and you are going to connect them together if they are going to be neighbors. So the question was, if you want to color a map of world, how many colors do you need? So that, you know, the different country would have different colors. So if you have 2 countries which are next to each other, they should have 2 different colors. It was predicted that you need only 4 colors to do it. So they call it 4-color problems. Of course, the way they do it, they call it the region. You know, if you look at the map, you have the United States of America, and then next to it, you have Mexico. So the Mexico and the United States would have 2 different colors, okay? And then we have Canada over there. So Canada, American, they are neighbor, so they should have different colors. So the idea was, in order to do it, you need only 4 colors. So this problem was the beginning of there are 2 historical problems. This is one of them. The beginning of the graph theory, really. And this problem was around for some times. Quickly, there was a guy, I think his name is Kempis, or Kempse, I think that's it. He's an Irish mathematician, and he was the chair of the London Mathematical Society. He quickly solved this problem, that yes, it's true, you can color any map of the world just using 4 colors. But unfortunately, a few months later, they find out that there is a gap in his proof. So he modified his proof, and he created something that he called it 5-color problem. With his proof, he proved that in order to color any map of the world, you need 5 colors. It was quite a lot, you know. I think it was in 1973 or 74. 2 engineers, if you like, or mathematicians, American one. They just prove it. They proved that yes, in order to color each map of the world, you need only 4 colors. The way they did it, I am a pure mathematician, so we are not satisfied, because the way they do it, they use the computer programming, and they proved it. They construct it. You see, they construct the map, and they show that you can do it. But up to today, we haven't seen any abstract proof of the fact that the 4-color problems would have a positive number, okay, positive answer. But anyway, it's interesting. This is your field. You better check 4-color problem and get the story really. So I have given you several examples of the great theorems that have been proved by some people who are not pure mathematicians. But it was quite a nice fun. I remember when the problem was solved, there was no internet. So in order to let everybody knows that the problem has been solved, when you receive a letter from a state, you see the stamps. The stamps, you read that 4 suffices. I remember that. So just let anybody knows that, yes, in order to, you can use 4-color to use the 4-color. But in order to get the proof, you need a couple of more things. So I cannot explain the actual proof for you. But it's a nice one. So that was something for you to motivate. So pay attention to this example that I'm going to give you. Okay, we give you one problem from this section that I talk about so far, and that's going to be a problem of the coloring of the graph. That's, it's been done quite a lot on this. They created some methods, but no abstract proof yet. Okay, that's it. Graph coloring. So what's a graph coloring? We call it a vertex coloring. That's it, a vertex coloring, or just coloring, or coloring of a graph G is an assigning or assignment. Okay, assignment of a color. Okay, of color to each vertex, of G, such that adjacent, the one's going to be neighbor, adjacent vertices have different colors. That's coloring of the graph. Okay, the minimum number of the colors. The minimum. Okay, minimum number of colors that we needed to paint or color. Paint G is going to be called the chromatic number. Okay, that's the expression. Chromatic number of G, and is denoted by this chi of G, if you like, chromatic. Okay, chi of G. So I'm going to give an example to show you how we do it. And then, we give you one. The one that we are going to give you is going to be scheduling the final exam for the college. We give different, name of the subjects, the exams. You are going to draw the graph yourself. The coloring would be the number of the days, the schedule, okay? Monday, Tuesday, instead of coloring. But you know that in scheduling, we need the same thing. So this is it. Let's do it. Let's see how we're going to do it. Example, we want to find the chromatic or coloring number. Chromatic number of the graph. G. So we give it the graph and you just tell us. So let me just get the graph done and then you can graph it yourself. So this is going to be the graph that we have. So it's going to be something you are going to do it for us. You draw the graph yourself and eventually it's going to be like this. So I'm going to have this is the vertices. It's a V1, V2, V3. Then I have the V4, V4, V5, V6. Okay, this is going to be 5, 6. Then I'm going to give you another one here. So this is going to be my V7. And I make one here, which is going to be V8. And then you have the following. There is a connection between these two. Okay, and there is a connection between these two. There's a connection here. Okay, a connection here. Then there is a connection here. And I have this one to be connected. And there is a connection between these two. And this is it, I think. And this one too. So the one that you are going to graph, the number of the classes would be given to you. You see if these two classes would have the same students, they share their students, so you just connect them together so that you color it differently. You get two different schedule. Okay, we said, it takes times the other one, so I need to have it. So we do it when we get to the review. But when we do it together, then the action is going to be now. Okay, just do it when you are ready. Just we can work out. So the best way to color it, just make sure you're not going to miss anything, is find the degrees first. Okay, we find the degrees first, and we start with the highest. Okay, we start with the vertex with the highest degree. Okay, because the highest degree give you all the connection, and you know that you can start with the V2 if you like. So if you color the V2, then you cannot use the same color for those which are going to be adjacent to the V2. That's why we start with the highest degree and just we keep going down. Okay, so the first thing to do for this must be, you have to find all the degrees and you have to show it on the test with these numbers. So find the degrees. Okay, find the degrees of all vertices. You just count the number of the number of the edges and identify the degrees. So I start with the V1. You say this is a degree of V1. It's going to be equal to the V1, 1, 2, 3. 3. Then I just keep going. V2. V2, you see 1, 2, 3, 4. Number of the edges. V3. V3, 1, 2, 3, 4 again. So that give you 4, then we just keep going. Degree of the V4, it's 3. Okay, then I go with the V5. V5 must be 6. 1, 2, 3, 4, 5, 6. It's going to be 6. Then that's a V5. Okay, the V6. That is the V6, which is equal to 4. Okay, then we go with the V5, V7. V7 is 5. 1, 2, 3, 4, 5. That's a V7. And the V8. V8 is equal to 3. You see, that's the first step. Okay, so the first step is going to be identifying the degrees. Then you better list these these vertices according to their degrees. start with the highest degree and just going down. Okay, so what we are going to do is we are going to list it and as an order set, if you like. So I'm going to write this one for you, know it. Order vertices, okay, according to the degrees, if you like. Degrees. So we're just going down, if you like. So I start with the one with the highest degree. Okay, the highest degree is V5. So this must be the first one, V5. Just cross out the V5. Then I need the 4. So we can call it a lot of 4, you know, just start with one of them. So I'm sorry, that was 6, then we get a 5. 5 is V7. So we get the V7. That's going to be your V7. Okay, then we don't have any more 5s. So we go with the 4s. So 4, we have, okay. So I have we have quite a lot. Okay, so it's going to be 4. We have the V6. It depends, you know, it doesn't matter how you write it down. Okay, so let's write it down as is. So that was we go with the 4. So I go with the V2. Okay, the V2. So that's 4. The order is not important. V3. Then we have a 4 again here. V6. Okay, so we're done with the 4. Then we get the 3s. Okay, so for the 3 we have the V1, degree of 3. Then we have the V4, degree of 3, and we have the V8. V8. You see, that's the order that we're going to have. Any question? So start with the highest vertex with the highest degree and just keep going. Now start coloring. Okay, so if the preferences of the colors are important, you just do it. Otherwise, so what I do is I'm going to pick my first color. This is going to be my first color, okay? First color. For the scheduling of the final exam, it's going to be first day. If the first day of the final week is Monday, you say Monday. So which of the exams are going to be given on Monday? So you start with the first vertex. Is going to be V5, V5. Then you go down in the list. You are going to use the same color for the vertices or for the vertex that is not going to be adjacent to the V5. You know that if you are going to be neighbor of each other, you cannot use the same color. Okay, so I just go on check. You see that's a V5. You see that's a V5. So the next one is going to be what? Is a V7. You see 5 and the 7, you cannot use it because they are neighbor. So we cannot use the V2 because they are neighbor. We cannot use the V3 because they are neighbor. We cannot use the V6 because they are neighbor. Okay, and we can use the V1. Okay, because the V5 and the V1, they are not going to be neighbor of each other. Okay, so I can use the V1. So as I go on, I cancel it out, the V1. Okay, then I cannot use the V4 because they are neighbor, and I cannot use the V8. So I can use the green color. Okay, I can green it here so you can see it. So I color the, okay, I color the V5 and the V1 here. Okay, so that's going to be the one. Any question? So you cannot use this color to get more vertices, so you need a new one. So we need the new one, so we go to the second color. Okay, so it's going to be the second color. Second color, second vertex. Okay, over here. So we start with the V7. V7. And then again, you just bring the vertex that is not going to be neighbor or adjacent to the V7. Okay, so that was the V7. This is it. This is the V7. You cannot, but with the V2, in fact, you can use the V2. You see V7 and the V2, they are neighbor. So we can use the V2. So we already got the V7 and the V2. Okay, so we go on V3, V7 and V3. V7 and the V3, we cannot use it. Okay, we go to the V6, we cannot use it. Okay, going to the V4, you see V4, we can use the V4 here. So the V4, you just call it, you will see it, the V4. Okay, and the V8, you cannot use the V8 because it's connected to the V7. Okay, any question? So that is what this is going to be. We are done with the second color, so we need another color. So we go to the third color. Okay, that's going to be good. Third color. So what's going to be the next one? The next available one. I'm sorry, I have to cross the. So we're already done with the V2 and the V4 out. Okay, so you start with the V3. You start with the V3, then the V3 and the V6. So this is V3. That's a V3. Okay, V3 and the V6. Okay, they are not going to be connected to each other. So we can use the V6. I'm sorry, where is the V6? That's a V6, yeah. We can use the V6. So that's going to be the V6. Okay, so we're done with the V6 and we can also use the V8. We can use the V8. So there you are. We did color it just using the three colors. So this means the chromatic number is going to be equal to the 3. The word of the map is different. The word of the map is something we call it planar graph. You see this graph. In the case of the different countries, the countries cannot have, you see the territory of each country must be one piece only. So in this case, this is not a planar graph because these regions are intersect. So for the map, we call it a planar graph. This is not a planar graph. So that's why we get the coloring number equal to the 3. So if you want to schedule an exam for this type of situation that you have, you need 3 days only. And these are going to be the subjects that you can put them together. Any question? So it's an interesting procedure. So we have a couple of them, we just do the review. It takes a little bit time for the quiz or the test. So just make sure to do it as a kind of the last example. But it's not bad. There is only one thing that it didn't happen on this one. You got to be careful. You see, when I start with the V5, I cut V7 over here. I compare everything to the V7. But when you write these, some of these may be adjacent to each other. So you got to be careful. So they cannot be adjacent to each other, or they cannot be adjacent to the V7. But if you put the mark, then you are not going to miss it. Okay, so that was 1.4 that we didn't do it before. Now you did the 1.4. Now then the next lecture, we can come back to the 4.9 and finish this chapter. Okay, 4.9, there are some theorems that we're going to prove something nice. Okay, and then we are done with this chapter 4. So I check to see where is going to be our quiz. So I post a practice quiz for you, and then we start moving on. I think your quiz is going to be next week, so you may have to review on Monday. I check it, and the assignment, everything, I will post it for you, so that we get. But we try to finish this chapter to give you that quiz, because there are a couple of easy theorems in the 4.9. The best one is if you add all the degrees together, the sum of the degrees is twice of the number of the edges. This is the only theorem that we have, and some interesting result. Okay, that's it. Any question? So have a look at those problems of the section that I told you, section of the contradiction. Some of them are nice. Okay, have a good one, and see you next week. I will finish your grading of the test, of course, over the weekend. So I post the result, then if there's going to be anything, then we can discuss.
Can you just let us know what homework you're going to be collecting for the quiz? And that's going to be on Wednesday.
Yeah, I have to check it. Yes.
Okay.
I check that one, and then I post everything for you.
All right. Thank you.
Yeah, I think the quiz is on Wednesday, so we practice on Monday, and it's going to be up to the end of this section. But I have to check the previous one, then I post the exact number for you. Okay, by tomorrow. Okay, have a good one, and take care. Bye-bye.
All right, thanks. See you Monday.
Bye-bye.
Thanks, Professor.
Thank you. Bye-bye.